Hi everyone, Dr. P here, and in this lecture we're going to take a look at the nature of energy. So I want to start off with a few definitions. All right, a bunch of definitions. Now, when I teach in person, I usually do a little demonstration. I ask, what is energy? And a lot of students say, as they learned in maybe their high school physics class, the capacity to do work. So then what I do is I'll push on something. I'll push on something. So, I've got normally I'd push on a table, but I'm here. I'm gonna. Have I done any work? Well, no, my notebook here is still intact. It hasn't exploded or anything. I haven't done any work on the appreciable work on the notebook. However, I've put in some effort, and I've actually probably, well, not by squeezing a notebook, but if I did that a lot, I'd probably, start to break a sweat or something. So we're going to define energy as the capacity to do work or produce heat. Okay. Now, there are some other aspects of energy that we need to define. One is the law of conservation of energy. And that is, energy is neither created nor destroyed in a chemical reaction. And I'll just abbreviate reaction RXN. We can have various forms of energy. One of those forms is potential energy. And often I like to ask students to come up with different forms of energy, and some students will say potential energy, some will say kinetic energy, some will say chemical energy, which is actually a form of potential energy, electrical energy, which is also a form of potential energy. And really, we can break down energy into really two forms, which are potential and kinetic. Potential energy is energy due to position or composition. So, for example, my pen on my desk here has less potential energy than if I hold it up in the air a little bit. And if I drop it, sorry, there we go. If I drop it, the potential energy turns into kinetic energy. So kinetic energy is energy due to motion. Now, there's also a form of potential energy which is energy due to composition, and that's where we find chemical energy. So I could take my glass of orange juice here and have a sip, and my body will convert the sugars in the orange juice, convert the potential energy of those sugars due to the fact that they are sugars, and my body will convert those to, well, heat for one thing, to keep me warm, and also so that I can move around, so kinetic energy. Speaking of heat, we need a definition for heat. So heat is kind of a, sort of nebulous, loosey-goosey thing. We talk about heat flowing from one place to another. And heat is not really a substance. Instead, heat is a transfer of energy between two objects due to a temperature difference. Okay, and heat always flows from hot to cold. Now, it becomes convenient to talk about a chemical reaction releasing heat or absorbing heat, but really what we're talking about is the absorption of energy. And we'll see a particular type of energy later on that we also refer to as heat, and we'll talk about that a little bit later. We can have work. Again, energy is the capacity to do work, and that's force acting over a distance. So, for example, if I push my pen along here, I am doing work. I'm applying a force to the pen over a distance. Now, there's a couple things to note here. Energy changes energy change is pathway, or if I can spell, pathway independent. So it doesn't matter how I get from my potential energy of my pen to this potential energy of the pen. I could drop it, I could move it up, down, move it around, and then to the bottom, or down on the desk. It only matters where you start and where you end. And we call that a state function. And a state function is a property that depends only on a system's present state. So energy is a state function. Now heat and work are not state functions because they are pathway dependent. Okay, now my energy, difference in potential energy from here to here, is independent of how much I move this around. However, the total work that I do is very dependent on how much I move my pen around. So it's important to understand that, for some properties it only matters where you start and where you end up. For other properties, it matters how you get there. Two more definitions. In thermochemistry and thermodynamics, we will study a system, and everything else is the surroundings. So a system is what we're studying. And the surroundings are everything else. and that's everything else in the universe. All right. A couple more definitions here. And in particular, we're going to start looking at chemical reactions now. Well, let me just make sure you guys got all of that. System is what we're studying. Surroundings are everything else in the universe. Okay. So if we look specifically at chemical energy, and if our reactions involve heat, that is the flow of energy in the form of heat, if energy flows out of the system, that is exothermic. And if energy flows into the system, that is endothermic. So we're talking about energy in the form of heat. And that specifically refers to the therm part here. Therm coming from Greek for heat, the Latin for heat. I really don't know. Now you have to remember that energy is conserved. So the energy gained by the surroundings must equal the energy lost by the system, or vice versa. So in an exothermic reaction, the potential energy of chemical bonds is converted to thermal energy, which is really random kinetic energy. Remember our kinetic molecular theory of gases. So the potential energy is converted to thermal energy via heat. And we can visualize this with energy diagrams. So we can plot potential energy on one axis here. And let's take a look at CH4 gas plus 2O2 gas reacts to give CO2 gas plus 2H2O gas plus energy in the form of heat. And that's just the combustion of methane. So initially we start with 2 moles of O2 and 1 mole of CH4. And then we end down here at 2 moles H2O and 1 mole CO2. And we have some change in potential energy. And that is the energy released to the surroundings as heat. And we call the study of energy, especially in terms of heat, thermodynamics. And we'll talk more about thermodynamics later on. We'll just touch on a little bit about it in this chapter, but we'll talk about it more in a later chapter. And one thing to know is the first law of thermodynamics, which is that the energy of the universe is constant. Okay, so we're not, that goes along with the law of conservation of energy, and also energy flowing, like I said, energy gained by the surroundings has to equal the energy lost by the system, etc. Now, if we looked at an endothermic reaction, so this one is exothermic. if we looked at a different reaction, let's do N2 gas plus O2 gas plus energy in the form of heat goes to 2NO gas. In this case, we're starting at a lower energy and going up to a higher energy. So we've got 1 mole of N2 and 1 mole of O2, and we have to absorb energy in the form of heat from the surroundings. Now, we can, if we want to, give these some other fancy thermodynamic names, not just potential energy, change of potential energy. So thermodynamics has all kinds of fancy names for different types of energy, etc. And so in this case, what we want to talk about is the internal energy. Let me get my black pen here. And this has the symbol of U, okay, capital U. And this is the sum of the kinetic and potential energy of all the particles in the system. And so our change in internal energy is equal to heat, which we're going to call Q, plus work. So Q equals heat, and W equals work. And one important thing to note is that the sign of a thermodynamic quantity indicates the direction of flow from the system's point of view. So, sign of sign of the thermodynamic quantities indicates direction of flow. Positive is into the system, negative is out of the system. So it's from the system's point of view. Okay. So, what else can we say here? Well, we can do all different kinds of work. And we've been talking about gases, so let's talk about work that gases can do. And that's going to be PV work, or pressure volume work. And this is work done by a gas through expansion, or on a gas through compression. Okay, so if we look at a cylinder, for example, and we've got some piston in the cylinder here, and we have some initial state, and we have some pressure, which is force over area pushing down, and we do some work, so this is where our old level was. We've got some change here in height, and so that's going to give a change in volume. So delta H times the area equals volume. So this is our final state. So again, pressure equals force over area, or force equals pressure times area, just multiplying both sides by area. So our work equals force times delta H, which equals pressure times area times delta H, which is just pressure times the change in volume, P delta V. Okay, so this guy here is our delta V. And this should be actually not V, but delta V, because it's a change in volume due to the change in the height there. So for an expanding gas, work is negative, and we would say work equals minus P delta V, because the gas is doing work on the surroundings. Gas is doing work on the surroundings. Okay? Now I think I'm going to leave it for there. We've looked at energy, we've looked at a whole bunch of definitions, and we've looked at a particular kind of work, pressure volume work. And in the next lecture, I'll introduce you to another concept called enthalpy, which we often use when we talk about heat, and then we'll start looking at calorimetry, so measuring heat. All right, well, until then, stay safe out there. Bye now.